So, also welcome from my side. My name is Philipp Reb, and as Dominik already told you, I will present the topic signal integrity, impedance matching in combination with BGA fan-out. First of all, I will tell you about the agenda of this webinar. We will start with an introduction about fine-pitch BGAs in combination with their impedance requirements. In the main part of the webinar, we will do the examination of different BGAs according to their impedance requirements. Therefore, we searched out, or we decided to show you 5 different, more or less most common BGA pitches. The first two are 1.0 mm pitch BGA, 0.8 mm pitch BGA. These are more or less the BGAs which are still possible to fence out with bladed through holes. Then we will go on with 0.65, 0.5 and 0.4 mm pitch BGA. And for them you will still need microwires for fencing them out. Last but not least, we will also tell you something about the advantages of microwires, even if you not need them, for example for the 0.8 mm pitch BGA, and why it could be useful to use them also there. So first of all, we will start with BGAs and their impedance requirements. So impedance-defined tracks, single-ended and also differential track pairs, need to be fanned out from the BGA. Typical requirements are 50 ohm single-ended or 90 ohm differential or even 100 ohm differential track pairs. The bandwidth on a PCB is normally between approximately 45 ohm single-ended up to maximum 120 ohm differential. Ideal is it to route the critical signals almost on the inner layers. Why? Because on the inner layers we have thinner and more constant copper thicknesses due to the fact that there is no galvanic process in the inner layers. So that means that the precision is much higher and you also have a very good EMC shielding. The type and the number of the connections, so also on the number of the rows leading to the number of the layers of the PCB, as the wire pad size is restricted. Therefore, please check our design rules. What needs to be considered according to the impedance in a BGA? For example, a 1.27 mm or 1.0 or 0.8 mm pitch BGA are normally possible without the use of laser drilled microwires. So possible track widths determined by the grid spacing and the pad size, and the number of the layers and the PCB thickness also depend on this. Therefore, please check our basic design guide you will find on our homepage in the internet. The 0.65 mm pitch BGA, therefore, is only possible by the use of microwires. Good thing is, here you can more or less use our HDI standard design rules. Here we also have a very reliable design guide in our internet with recommendations for all common BGAs. In the end, we will also show you something about 0.5 and 0.4 mm pitch BGAs, and they are also only possible to fence out by the use of microwire. But here it needs to be considered that we can maximum work with a layer distance of 60 to 70 micron. So for example, 50 and 100 ohm signals should be routed here even on the core layers below the microwire layers. But if there's no other possibilities, it may be also possible on the microwire layers, but in this case you need to use fine line structures below 100 micron track width. So first of all, we will take a look on the 1.0 mm pitch BGA and the 0.8 mm pitch BGA. Here it needs to be considered that in the most PCBs with less than 12 layers, it's even possible to work with 35 micron copper on the cores. For high layer PCBs with more than approximately 12 layers, it could be needed to work with 70 micron copper, especially if you work with a defined PCB thickness, for example 1.6 mm or less. The good thing with 17 micron copper is that you also have the possibility to work with smaller structures and even with smaller layer distances due to the impedance requirements. Important is always that you consider also the pad sizes or the limits of the pad sizes and the aspect ratio rules according to our design rules. These you will find in the basic and even in the HDI design guide. This is needed to have a high reliability during the thermal cycles in the wire. So that means that the wires are more stable due to the better copper in the barrel, and therefore you have a higher reliability. So let's take a look on the 1.0 mm pitch BGA with bladed through holes. So due to the restrictions of the wire pad size, the number of the rows that need to be fanned out leads also to the number of the signal layers that are needed in the stack up. And the number of the layers determine which layer distances are needed. And even these layer distances and the epsilon R value of the materials lead to the track widths you can use and even to the gaps in the differential pair. So depending on the layer count, there are different possibilities to dimension the track widths and gaps between the tracks. That means that you have more possibilities to dimension the tracks and gaps if less layers are needed in the stack up. So in a 1.0 mm pitch BGA, you are possibly able to route 2 tracks in between the pads, but only with 100 micron dimensions. So 100 micron track and space in between the tracks, and even 100 micron distance to the pads. That means that the track widths and the gaps need to be dimensioned correctly outside the BGA area to match the impedance requirements of them. So let's show you some examples on the outer layers for a 1.0 mm pitch BGA. If you work, for example, with a 2113 prepreg, you can use more or less standard track and gap parameters. For example, 50 ohm with a track width of 153 micron, or 100 ohm differential pairs with a track width of 100 micron and a gap in between of 142 micron. As you can see, the thicker the prepreg becomes, the bigger is also the track width. For example, let's take a look on the last sample on this page. If you use, for example, 2 times the 1080 prepreg, you will reach with 237 micron track width 50 ohm. But as you can see, with higher layer distances, it is also possible to route more or less more exotic values like 120 ohm with more or less standard values like 100 micron track width and 200 micron gap in between. Even on the inner layers, I will show you some samples. As you can see here, by the use of a 150 micron core and 2 times 1080 prepreg against the next plane layers, it is still possible to route, for example, this 110 micron track width for 50 ohm, or 100 micron track width and 230 micron gap for differential pairs with 100 ohm. 90 ohms are even more or less less critical than 100 ohm. Further, as you can see, here we also have the same effect as we have from the outer layers. The bigger the layer distances are, the bigger are also the track widths. But here it is also more or less possible, as you can see in the last line, that also you can route, for example, 120 ohm differential with a track width of 100 micron and a gap of 350 micron in between. So let's go on with the 0.8 mm pitch BGA. As I already told in the beginning, you can even route an 0.8 mm pitch BGA by the help of bladed through holes. But even maybe microwires can be useful. In general, if you use bladed through holes, you can use more or less the same stack ups like you use in a 1.8 mm pitch BGA. But depending on the BGA size, maybe microwires could be useful. As with microwires, you have much more space in between the pads, as we can use much smaller pads by the help of laser drilled microwires. For example, with bladed through holes, you are only able to route 1 track with 100 micron in between the pads, but even on the inner layers. So therefore, I will show you a design study why maybe microwires could be also a useful option if you have a very, very big 0.8 mm pitch BGA with a lot of connections to be fenced out. If we have, for example, an BGA 0.8 mm pitch BGA, and let's think about that maybe every pin has to be fenced out. And we have a BGA with 20 to 20 rows. So how many signal layers are possibly or maybe needed to fence out this BGA? As you can see, there are many signal layers needed to fence out this BGA. In this case, it is needed to use 7 signal layers to fence out such an BGA. But if you take a look on the microwire technology, as you have more space in between the pads to route, you need only 3 layers for the same BGA to route it out. So that's maybe a case or an option to think about if you have a very complex 0.8mm pitch BGA or bigger, to start with the use of microwires. So even later in the webinar, I will show you some further advantages of this technology. So if we take a look again on the outer layers of an 0.8mm pitch BGA, I also want to show you some samples. Maybe here the first one is still the most interesting one. By the use of a 1080 prepreg, so a very small distance to the outer layers, it is possible to route 50 ohm with 110 micron track width, so very similar to the 100 micron you can use in between the tracks. So the depth of the line outside the BGA is not that big. The other samples you already remember I showed you still for the 1.0 millimeter pitch BGA, as more or less the circumstances regarding the stack-up are the same. If we take a look on the inner layer, you will see that I will show you here also the same samples than for the 1.0 millimeter pitch BGA, because on the inner layers you can use, for example, more or less every BGA the same values. So in general, the depth of the short tracks that are impedance defined are not that critical. The long tracks always need to be adapted, but we also recommend to make an impedance matching even on the short tracks if you're still doing it also for other tracks. You will only have advantages. So let's go on with the 0.65 millimeter pitch BGA. Here it is definitely needed to use microwires for the fan out of the BGA. Here you can see on the right side and more or less advice on our HDI design guide, because in this BGA it is still possible to route or to work with HDI standard design rules. For example, in pad size of 325 to 350 micron and with a track width of about 100 micron, and even the solder mask clearance is here in the standard area. If you take a more detailed look on this 0.65 millimeter BGA, as I already told you, the BGA fan-out is only possible by the needs of microwires, but the good thing is here that we can work more or less with our so-called deep microwires with the 2113 or the 2116 prepreg with a layer distance of 90 to 110 micron. So that means that also 50 and 100 ohms are possible on the microwire layers. And you can still use 100 micron track width, and this is still standard for our company. So critical signals, as I already told you in the beginning, should be routed on the core inner layers below the microwire layers. Advantages are thinner and more constant copper thicknesses, so the precision is much higher, and you even have a good EMC shielding. And you even have more possibilities to control the layer distances, and therefore more possibilities to fulfill your impedance requirements and the track widths you need. The fan out should be done ideally with the combination of microwires and buried wires if you still need them, and the minimum microwire pad size for these technology is 325 micron. Here we also want to show you some samples for the outer layers and even for the microwire layers on the first inner layers. If you take a look, for example, on the outer layers, by the use of a 2113 prepreg, you can more or less still work with standard values. So even for 100 ohm differential, you can work with 100 micron track width and 137 micron gap in between. On the inner layers, as you can see here with the parameter S2, you can even use more or less standard structures, but as you can see, it is still more critical due to the small layer distance to the plane layer above the signal layer. So here it is also recommended, if possible, to put the critical signals on the inner layer. With more or less the same circumstances you can also have for the other BGAs, for example 150 micron core and 2 times the 1080 prepreg. So Again, 50 ohm can be routed with 110 micron track width, and 100 ohm differential can be routed with 100 micron track and 230 micron gap in between. But maybe in many cases you need many signal layers to fan out your BGA, especially if you have many pins to connect. So in some cases it could be needed that you even have to put two signal layers above each other. Here you should route on the different layers with XY to determine the crosstalk as much as possible. But here, for example, if you using 150 micron core in between the two signal layers and the 2116 pre-break to the next plane layers, you can even route with standard values, for example, 128 micron for 50 ohm single-ended, or 100 micron track and 155 micron gap in between for 100 ohm differential track pairs. So now we will go on with the 0.5 mm pitch BGA. And here we need to consider that even here also the fan out is only possible by the use of microwires, which is still clear as you still need them for an 0.65 mm pitch BGA. But here we need to consider that we have very small layer distances on the microwire layers, as we need to work with very small pads. Therefore, it is only possible to work with a 1080 pre-break with a thickness of about 60 to 70 micron in between the signal layers. So depending on the layer order, very fine line structures are needed to route the most common impedance-defined structures on these microwire layers then. So that's why we especially here recommend to route all the critical signals on the core inner layers below the microwire layers, as you can see also for the other BGAs. Advantages are again better EMC shielding against external sources, and ideally you do also the fan out of the complete BGA with microwires in combination with mechanical drilled buried wires. So therefore, you will only also have the advantages that you have less reflections than you have with plated through holes. So now I will show you a foil. What does it mean to have less reflections than with plated through holes? Here I want to show you some discontinuities in possible wiring schemes. If you take, for example, a look on the version 1, here the fan out or the signal ways are routed with plated through holes, and you can see here you are not able to build a direct signal path with the wires, as you always have the rest of the drills that lead to reflections. That's what we also call open-end antennas. If you take a look on the right side, on version 2, you can see here the signal ways are built with the use of microwires in combination with buried wires, and you can already see that it is possible to have a direct signal path. So blind and buried wires results in reduced discontinuities. So that's why our recommendation is always, if you're still using microwires and buried wires to route your BGA, we always suggest you to replace as much plated through holes as possible, because you will only have advantages therefore, especially regarding impedance-defined tracks. So on the left side you can see our recommendations to route an 0.5 mm pitch BGA. As you can see, you need to use these 275 micron tracks to make it possible to route latest on the inner layers with 75 microns in between the pads. The solder mask clearance here that is needed is 35 micron. So 75 micron structures are possible in between the pads. And here I also want to show you some samples for the outer microwire layers. So as you can see here, due to the fact that we need to use reduced copper thickness on the outer layers, if 75 micron structures are needed, it is still possible to route impedance-defined tracks on the outer layers with more or less standard values. So 123 micron track width for 50 ohm single-ended, or for example 100 micron track width and 168 micron gap for 100 ohm differential. But on the inner layers you can see that it's even more restricted due to the small layer distances, the layer distance regarding the microwire to the next plane layer. So here, for example, for 50 ohm, 75 micron track width is needed, and maybe in some cases 100 ohm are still not possible, even by the use of 75 micron structures. But we always recommend to put the most critical signals, as I already told many times in the webinar, to put them on the signal layers, on the cores below the microwire layers, as it is not recommended to use much smaller tracks than 100 microns, because the tolerance of the track width will influence the impedance much more than by the use of a little bit bigger track widths. If we take a look on the BGA 0.4 mm pitch, you can see that it is still not possible to route tracks in between the pads, as the limit in pad size is 275 micron, and we need to put enough solder mask in between the pads that the PCB will be less critical during the solder process, and you have a higher reliability in your assembling process. So regarding the impedances, you can use more or less the same layer stack-ups than you use for 0.5 mm pitch BGA. And here it's also recommended again to put the critical thickness on the core inner layers below the microwires. The fan-out in combination of microwires and buried wires is again the best way. But here you even have the possibilities maybe to make the fan-out of some of the connected pins with plated through holes outside the BGA area. Now we still take a further look on the inner layers for 0.5 mm and 0.4 mm pitch BGA regarding the impedance requirements. If you need to use, for example, many layers to fan out your BGA, it could be maybe needed to work with very small layer distances of about, for example, 100 micron. But here you can see directly that you even need to use for 50 ohm single-ended still 90 micron track width. 90 ohm are, as always, less critical, but if you take a look on the 100 ohm requirement, you can see that it is here definitely needed to use track widths below 100 micron. So as you can see on the left picture, for example, for an 0.5 mm pitch BGA, where it is still possible to route tracks in between the pads, it is needed to dimension the track width outside the BGA regarding the impedance requirements correctly, as it is only possible to route 75 micron in between the pads. So, but we always recommend, if possible, due to the PCB thickness and the layer number, to use bigger layer distances even here on the inner layers, as the impedance tracks are then more reliable and it is easier to hold the tolerances. For example, again, if you use a 150 micron core and 2 times the 1080 pre-break, here in this combination with 17 micron copper, you can use, for example, 122 micron track width for single-ended 50 ohm, or for example 100 micron track width with a 150 micron gap in between for 100 ohm differential line pairs. So as you can imagine, regarding the BGA size, we are already at the end of this webinar. And last but not least, I will give you the summary. So in the fan out of BGAs, impedance requirements of the components need to be considered. In general, critical signals should be routed on the inner layers, as I told you many times during this webinar. BGA pitch with 1 mm and 0.8 mm and larger can be routed with the help of plated through holes. Therefore, you have more or less restrictions on the layer stack-up. The smaller BGAs, which need to use microwires for the fan-out, will lead even to more restrictions in the layer stack-up due to the microwire layers that are needed. Then it is always, as I still told you, very important to use the correct pad sizes and aspect ratio rules from our design rules. And this needs to be considered that even in the BGA fan-out, the reliability of the wires is very high, especially due to during thermal cycles in the assembling process. And Würth Elektronik is always ready to support you with an individual stack-up up according to the needed BGAs. So if you have special requirements, always feel free to contact us, and we will help you to find the ideal stack-up to fence out all your BGAs. as we had some questions, we take a look on the most asked questions we had during the webinar. One of the questions was, is it useful to work with plated through holes directly in the BGA pads? Therefore, the answer is no, if possible not, because if we have the plated through holes directly in the pad, we need to fill the wires and overplate them, and therefore we have to count some additional costs as we have some more processes in the production to fill them and overplate them. A further question was, what is the biggest layer distance you can realize with micro wires? And the answer here is the biggest layer distance we can realize with the help of micro wires is approximately 110 micron by the use of a 2116 pre-preg. Further question was regarding all these PCB things. Maybe as the last webinar, as long time ago, the question is: Würth Elektronik also possible to make impedance measurements on the PCB? The question is yes, but therefore we need to bring in some test coupons in our production panels to measure the impedances later and have a good adaptation. And this measurement has to be ordered by you. So that were the most asked questions, and then I will give back the word to my colleague Dominic Waltz. So in this case, thank you from my side, and I wish you a nice day.